Welcome to a little mathematical wonderland. Not quite as wonderlandy-ful as chapter 3 is, but we got a math section. But hang in there. It's not going to be that bad. And we'll get to some cool results near the end that has to tie in with combinations. Okay, so you ready? Let's go back to algebra. So if I wanted to expand x plus y squared, remember what that is x plus y times x plus y. We could FOIL it out. Did anyone see the FOIL bird? I don't remember how to write the FOIL bird, but I saw that first, outer, inner, last. We do that. We collect like terms, and we get this. Well, if we wanted to take that to the next step, we could find x plus y cubed. And if we did that, we would expand it all out, and we would get this. We could find x plus y to the fourth. We'd expand it all out and get this. We could find x plus y to the fifth. We could just keep on going on and on and on and see this. Now, all of these coefficients are known as binomial coefficients. So remember, the coefficients are just the numbers in front of the exponent. So it's 1, 2, and 1. Then 1, 3, 3, 1. And then 1, 4, 6, 4, 1. And you're going to see, if you've not already experienced it, a pattern here. When you expand a binomial, x plus y is a binomial. It's something plus something else. When you expand it to some exponent, you get these very special coefficients. And we could draw these coefficients. If you raise something to the 0th power, it's just 1. If you raise something to the first power, x plus y, each coefficient is just 1. And now we're squaring things. So now we're finally getting to what we're talking about. We had a 1 and then a 2 and a 1. Then we had the 3rd power. These were the coefficients. We had the 4th power. These were the coefficients. And you have probably seen this before. What is this? This will go on forever. No, it's not a Christmas tree. Oh, that kind of looks like a Christmas tree like this. This is Pascal's triangle. All right. And it's really nice because, first off, binomial coefficients tied to something called the binomial theorem. It's actually tied to a theorem that tells us that if I wanted to write this for some ungodly reason, I could very easily with the binomial theorem. We'll get into that later. A little excitement for the future on how to do that easily. I know y'all are probably really curious, but we'll save that for later. And again, this is nice because every number in the triangle is just the sum of the two diagonal numbers. Think of like a upside down binary tree or something like that. So every child is kind of the sum of its two parents. I don't know. It's just a weird way of saying it, right? But that's the idea how you can construct it. So you could keep on constructing this by just saying, oh, okay, what's 1 plus 5? It's 6. What's 5 plus 10? It's 15. And so on. You can make this tree grow as big as you want, as big of a Christmas tree as you want. How tall is your ceiling? I'm recording this about a month and a half before Christmas, so jumping the gun a little bit. But yeah, it's kind of fun. It's Pascal's triangle. And if we call this row 0, and if we call this row 1, these are the exponents, right? This is really x plus y to the 0th power. Any number to the 0th power is 1. This right here is really, what x plus y to the 1th power is. It's 1x plus 1y, and so on. So if we call these rows, then we have something very cool. All right. And specifically, it's that the numbers in row n are just n choose I. So, whoa, combinations. Pascal's triangle has to do with combinations. Who would have thought that? What a crazy thing that we would be talking about Pascal's triangle right after the video on combinations, because these are just all the numbers for basically, you can use Pascal's triangle to find any combination. You want to find what 100 choose 26 is? Just make Pascal's triangle and look at the 100th row. It's that easy. Might take a while, but you can do it. All right. So, but that's pretty cool. All right. And specifically, this leads to some interesting visual results as well, because you've probably noticed that Pascal's triangle is symmetric, right? Everything to the left of here is the same as everything to the right of here, which gives us some kind of cool conclusions about symmetry as well. Okay, right? So, that's not how you write an S. Not quite. We have some cool symmetry, right? So that's going to tell us, essentially, that if we have something like, 10 choose 2, that's going to be the exact same thing as 10 choose 8. Because, again, this is kind of the 0th spot, the 1st spot, the 2nd spot, the 3rd spot, the 4th spot, the 5th spot. So if we are on the 8th row, this would be the 3rd to the right for 2. Third from the left would be a 2, and 3rd from the right would be 8. These are going to be the same. And mathematically, it definitely makes sense that they are the same, right? What's the formula? It's n factorial divided by n minus k factorial times k factorial. So if you switch k, it just switches the 8 and the 2 here. But it's still the same number, right? And logically, it makes sense that these are the same too, right? If I have 10 things and I need to choose 2 to grab, well, whether I grab 2 and leave 8, or I grab 8 and leave 2, it's the same number of ways I can do that, right? Grabbing 8 is always the same as leaving 2. So some cool symmetrical things for how combinations work that we can visualize with Pascal's triangle. And some really cool applications for something like this. It turns out, by the way, here's the binomial theorem, a little bonus mathematics for all of you. A little bonus math is that, let's say that we have x plus y to any exponent. Well, to find that, all you have to do is sum up all the things from 0 to n that look like this. N choose let's use k. Make it k. N choose k times x to the k times y, that's right, to the n minus k. All right, that's so ugly. That's the binomial theorem. We're not covering that. But it is a cool way, cool with a K. It is a cool way to expand some really big things. Okay, so let's just get some practice in, and then we'll move on, and I'll stop geeking out about math. All right, so, one more thing. Because of symmetry, right? We really only need half of the triangle, which is really, really nice for like a lot of like, I don't know. I always think whenever we don't need more than necessary, need more than necessary is a bit redundant, right? But whenever we have redundant information, whenever we have symmetry in like any type of mathematical, computer science, or algorithmic context, if you have symmetry, that's half the data that you have to store, roughly, right? It's half the memory required for something, because if you know you have that symmetry, you can always convert it. Which is nice, especially for really, really large problems. Again, especially in the mathematical side that I'm the most familiar with, but I'm sure it's the same for computation stuff, right? There are so many things that are just so big that, yeah, we can do it, but we really want to do it in the simplest way possible to save on time for algorithm runtime, as well as memory constraints and requirements on that. So that's the last cool thing I wanted to say about Pascal's triangle. So just a little practice with some of these concepts. I know you can find these all out very easily, but just to really reinforce some things, what does 500 choose 0? Without a formula. If there are 500 things, how many ways can you choose none of them? There's only one way to do it. Grab nothing, there's 500 left. That's the only thing you can do. It's 1. Another way to get 1 is remember that in row n, the numbers are that. So in row 500, space 0, what does a coefficient look like? Well, I don't have to come up with row 500 to know that the space on the left is going to be a 1. So that's another way to tie in this little fact here. All right, and furthermore, if I asked you what is 500, choose 500, we said that's symmetry. We said, I know this is symmetric. Whether choosing 0 and leaving 500 or choosing 500 and leaving 0, it's the same as long as the order doesn't matter. Okay, so yeah, whether I grab 0 and leave 500 or whether I grab 500 and leave none, there's only one way to do that, assuming order doesn't matter. So we have that symmetry here. Similarly, right, 10 choose 4, we could calculate that. It's 10 factorial divided by 10 minus 4 factorial divided by 4 factorial. All right. And again, we could do some shortcuts. We could do this by hand if we really wanted to, right? But, right, because this part is just like the falling, 10 to the 6th falling, remember? Or 10 to the 4th falling. Yeah, because there's 4 numbers. Still getting used to that notation, but either way, we can find this all out. 10 choose 4 is the same, well, spoiling a little bit. 10 choose 4 looks like this. It's 210. And so similarly, right, if I asked you what 10 choose 6 is, you know it's 210. Grabbing 4 and leaving 6 is the same as grabbing 6 and leaving 4 in terms of combinations. So let's end with a couple more examples. How could you quickly decide, because I can't avoid the math. I got to give a little math in here, but honestly, you could stop the video now. If you're on a time crunch, stop it now. But this will be short. How could you quickly decide if this equation is true or false? You don't have to do it all out. Let's just look at the coefficients. What are the coefficients? 1, 6, 15, 20, 14, 5, 1. What's wrong with the coefficients here? They're supposed to be symmetric. All right? It needs to be symmetric. So we could fix that. I'll just tell you that these are the right the first half were the right coefficients. So if we fix the coefficients, then it's true. And we can use that to find 6 choose 3 without the formula. Right? This is row 6 of our Pascal's triangle. So this would be 6 choose 0 would be that coefficient. 6 choose 1 is that coefficient. 6 choose 3, 6 choose 4. Sorry, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, 6 choose 6. So 6 choose 3 must be 20. And it's 20 because the numbers in row n are n choose I, or n choose k if you'd like. So the answer is 6 choose 3 equals 20. So it's just another way that these concepts tie together. Let me know if you have any questions about this, and thanks for giving me a little chance to talk a little bit more about math.